Um, so chapter 8 is what we'll be talking about today, which deals with chemical composition. And in this chapter, I will be introducing to you some terms which will become very important later on. I'm assuming again that you'll have watched the videos concerning this chapter. So I'm just going to briefly go over a certain amount of, certain number of concepts. And at different intervals, we'll be looking at questions in assignment number 8 for this chapter, right? So the first thing I want to talk about here is the mole concept, all right? Now, I'm quite sure you guys are familiar with, in your everyday interactions, the term dozen, right? So, right? Right? This term is used every day, and we all know what it means. It means 12. Right? So a dozen items will mean 12 items. Right? So it's one of those counting terms, all right, that we use and everybody understands what that means. All right? Well, the mole in chemistry is kind of similar to that, with the exception that the mole is a number that is significantly larger, or it represents a number that is significantly larger than 12. I can tell you that for sure, right? So the mole concept is important because of what is stated here, and that is that an atom of any element is too small to measure on a conventional balance. And just to give an example, the mass of the hydrogen atom is this right here. As you can see, it's a very small number, right? Some other terms I need to talk about. The atomic number, which we discussed already, but just to remind you, is the number of protons in the nucleus of an atom of an element, and each element has its own unique atomic number, and the mass number is the sum of the number of protons and neutrons in an atom. And then we get to the atomic mass. The atomic mass is the mass of the atom expressed in atomic mass units, right? And that's that the atomic mass unit became necessary because, again, atoms are very small, so therefore we need a smaller unit than the conventional grams or pounds or whatever. And the definition of one atomic mass unit is 1/12 exactly the mass of a carbon-12 atom. And it turns out that one atomic mass unit is equal to this value right here. All right. And this last sentence here, I won't delve into it much, but basically, and this might seem a bit counterintuitive, but basically what this is saying is that the mass of an atom is not exactly the sum of the mass of all the particles that are present, the protons, neutrons, and electrons. There's a reason for that, which I won't get into. For those of you who have to do general chemistry too, you're going to learn about the reason why this is true, right? So going back to the mole concept, because in reality, if you have a reaction taking place, even for a small amount of substances involved, the number of atoms involved is relatively large, right? So the term that is used by chemists in order to take into account these huge numbers, we call that the mole. And by definition, the mole represents this number here, 6.02 times 10 to the 23. So that's a very, very large number, as you can imagine. And in fact, I think I have some information here which basically illustrates. Oh, by the way, that number, 6.02, is also known as Avogadro's number, all right? Named after the famous Italian scientist. And just to give a picture as to what we're talking about here in terms of the Avogadro's number, it says here, if 10,000 people started to count Avogadro's number and counted at a rate of 100 numbers per minute, each minute of the day, it will take over 1 trillion years to count the total number. So that gives you an idea as to how large that number is, right? So by definition, 1 mole of any element contains that number of atoms of that element, all right? And it turns out that we have another term known as the molar mass, which represents the mass that is that 1 mole of an element or an atom would have, right? And it turns out that the molar mass is the same thing as the atomic mass for elements, right? But numerically, they are different. The difference between them is that, well, not numerically, they're different. They're numerically the same, but the units are different. That's what I meant to say, right? The difference between them is that the atomic mass unit is expressed in AMU, and the molar mass is expressed in grams per mole, right? So for example, if I take any arbitrary element like, let's say, sodium, sodium has, according to the periodic table, the atomic mass of sodium is 22.99 AMU. Well, we can say that the molar mass of sodium is 22.99 grams per mole, right? So I think I have some other examples here. Okay, so that's basically talking about the relationship between the atomic mass and the molar mass. They're numerically the same, but the units will be different. Units of atomic mass is AMU, the units of molar mass is grams per mole. And then there's a list of examples of different substances, not only elements, but compounds as well, like benzene, C6H6. 1 mole of this will contain this number of molecules of that compound, for example, all right? So here's the relationship between the mole and Avogadro's number. 1 mole of atoms will have this number of atoms. 1 mole of molecules will have the same number of molecules. 1 mole of ions will have that number of ions, and so on and so forth, right? So it doesn't matter what we're talking about. And we can literally apply this to pretty much any object. You can have 1 mole of oranges, 1 mole of cars, 1 mole of chairs. But of course, in chemistry, we apply this to atoms, molecules, ions, and so on, all right? So just to reiterate, the molar mass of an element is its atomic mass expressed in grams per mole, right? And it contains Avogadro's number of atoms of that element, right? And just to give you some examples here, hydrogen has an atomic mass of 1.008 AMU and a molar mass of 1.008 grams per mole, but they contain the same number, well, in per mole, the number of atoms would be 6.02 times 10 to the 23. And we have corresponding numbers for the other elements, magnesium and sodium, but what they all have in common is the number of atoms per mole, all right? Even though the molar masses will be different. Now, before we do this, let me get you started on the first question in assignment 8. Let me just check something here. Okay, so there's only one person in class here. I'm going to give that person assignment 8. And I want you guys to focus on part 1. Right? Now, for you guys out there in Zoom, I am going to now publish assignment 8. So let me go here. We go here. Here. Okay, so assignment 8 is now published. Let me just open that up. And basically what assignment number 1 in assignment 8 is asking for you to do is to calculate the molar masses of the different substances. So I'm going to help you out with the first one, and you should be able to do the others based on that. So in the case of the first one, the molar mass of sodium bromide will be equal to 22.99 grams per mole for the sodium, plus for bromine, the molar mass of bromine is 79.90. 79.90 grams per mole. And let's see what that gives. So according to my calculation, this works out to be equal to 102.89 grams per mole. And that's basically what I expect you to do for each of these, all right? Now, of course, in the case of something like lead 2 sulfate, let me do that one. Lead has a molar mass of 207.21, according to the periodic table here. So 2.71 grams per mole, plus sulfur, which is 32.07. Oh, I made a mistake. That should be 207.21. And transpose these numbers here. So this should be 207.21. 207.21 grams per mole. And for the sulfur, that's 32.07 grams per mole. And then we have 4 oxygens. So what that means is that we have to multiply the molar mass of oxygen by 4, which is 4 times 60.000 grams per mole. And then we work this out. So let's see what that gives. 4 times 16, and then I add to that 32.07, and then I add to that 207.21. So according to my calculation, this works out to be equal to 303.28 grams per mole. All right. So based on what I've just done, you should be able to do that. So I want you to do that right now. If you have any questions, feel free. So basically, I expect you to do questions 1 through 6. Right? I want you to do that now because you need to know how to do that in order to do some other problems you're going to look at. All right? Okay, I take it you guys out there in Zoom are finished as well with number one or part A of the assignment, number 8. So let's go to the PowerPoint and talk about what's next. Okay, so based on what we have covered so far, let me get rid of this here. We now should be able to do some problems involving calculating things like number of atoms, number of moles, and so on, based on the relationship between Avogadro's number, molar mass, and mole, all right? So here's one example. This question says, it's right here. This question says, how many iron atoms are contained in 25.0 grams of iron? So the way I would approach this problem is that I would start off with the mass in grams of iron, and then I'll convert that to moles, and then I'll convert that to the number of iron atoms. All right, now to get from grams to moles, you would use the molar mass here. And to get from moles to the number of atoms, you would use Avogadro's number. All right, so let me set this up, 25.0 grams of iron. Now to convert from grams to moles, as I said before, we'll be using a molar mass. Now the question is, how do we represent the molar mass here? And the answer is that we basically put the gram value here and 1 mole above. All right, so the molar mass we can get from the periodic table, and that would be equal to 55.85. So this would be 55.85 grams of iron. And then we would have successfully obtained the value in moles up to this point, but we need to take another step where we need to determine the number of iron atoms. So, of course, that would be Avogadro's number involved. And the way we would set this up here is that we would have 1 mole of iron below, and Avogadro's number above, which is 6.02 times 10 to the 23 iron atoms. And let me just say that for all purposes, we're just going to round off Avogadro's number to 3 sig figs, 6.02 times 10 to the 23, all right? So that's set up. This will cancel out with this, and then we do the number crunching. So 25 divided by 55.85 times 6.02 times 10 to the 23. And according to my calculation, when rounded off to 3 sig figs, that will be 2.69. And folks, please correct me if I'm wrong. Make sure you do the calculations along with me, so that if I make a mistake, you can point that out. But according to what I got here, the answer is 2.69 times 10 to the 23 iron atoms. Right? And that's basically how that is done. Okay, any questions about this? Any questions? Any questions out there in Zoom? No questions. Let's move along. I think the next slide is another example. Yeah, okay, now in this case, they're asking, in this case, they're asking, what is the mass of 3.01 times 10 to the 23 atoms of sodium? So this is the reverse of what we just did in the previous example. In the previous example, they gave us the mass and they're asking for the number of atoms of iron. In this case, they gave us the number of atoms and they're asking for the mass of that collection of atoms. So basically, we're going to start with 3.01 times 10 to the 23 sodium atoms. Now, my question to you is, what do you think I need to multiply this by in order to carry out that conversion? There are two steps involved, just like we did in the previous example, but the previous example is the reverse of what we're doing now, all right? So what will you multiply the 3.01 times 10 to the 23 by? In other words, what would be the numerator up top and what would be the denominator below? So what say you guys? Let me give you a hint. So how would I convert this to moles based on what we did before? They gave you the number of atoms. What would be the conversion factor?
Would it be moles, 1 mole of sodium over Avogadro's number?
Yes, sir. 6.02 times 10 to the 23 sodium atoms. Okay, who was that who said that?
Ashton.
Okay, I just want to give credit to whoever say what they say. Okay, so thank you, Mr. Martin. So he's right as far as for some reason. Okay, so he's right. This is the setup, and this will cancel out with that, right? So up to this point, we would have determined the moles of sodium. But remember, the question is asking for the mass of sodium. So that means that we need to multiply by another conversion factor. So what would that conversion factor be? Well,
22.99 over.
I'm sorry, repeat that.
Oh, I didn't know my mic was on. It would be 22.99, which is the atomic mass of sodium over 1 mole.
Okay. Okay, so the only thing I would add to what you said is that this part here should
Oh,
be
grams per mole.
right. Okay, so this will cancel out with that. So your final answer would be grams of sodium, which is what the question is asking for. So let's do the number crunching, 3.01 times 10 to the 23 divided by 6.02 times 10 to the 23 times 22.99. And according to my calculation, this works out to be 11.5 grams of sodium. And that's how that is done, all right? Any questions about this? Any questions? Okay, so let me see what comes up next. Okay, here's another example. What is the mass of 0.365 moles of tin? Now, this one is actually easier than the previous two because basically you're given the moles and you're asked for the mass, right? So 0.365 moles of tin. So my question to you is, how would you solve this problem? What would you multiply the mole of tin by to get the mass in grams? Well, one goes up top and one goes below. Okay, well, somebody should be able to do this. What goes down here? Let's start with the denominator.
One mole or
1 mole of tin. And what goes up top?
uh 188.71 grams.
The mole mass of tin is, I see 118.71. Okay. That goes here. 118.71 grams of tin. And that's it. That's all we need to do, because what's gonna happen is that the moles of tin here and here will cancel out. So that would be 0.365 times 118.71. And according to my calculation, this works out to be equal to 43.3 grams of tin. That's it. That's how you work with that, right? Okay, any questions about this one? Any questions? Questions? Okay, now let's look at this one. It says, how many oxygen atoms are present in 2.00 moles of oxygen molecules? All right. So they gave you 2.00 moles of O2 molecules, and that would be equal to how many oxygen atoms? All right. Now, what I would do in this case is that I would convert from moles of oxygen to molecules of oxygen. All right. And then from molecules of oxygen to oxygen atoms. All right. So let's start off with the 2.00 moles of O2. And my question to you is, how would we convert from moles of O2 to molecules of O2? In other words,
Avogadro's number.
I'm sorry?
Avogadro's number.
Okay, very good. So how would you represent that in this conversion factor right here?
Moles will be one mole would be the denominator, and then 6.02 times 10 to the 23rd power for the
And this would be molecules of O2, all right? So that this unit will cancel with that unit, right? The next step is going from molecules of O2 to the number of atoms of O2. So my question to you is, how would we represent that in the next conversion factor? What would go below and what would go below? And the hint is in the formula.
it would
Because the
be
formula tells you that there are 2 atoms of oxygen per 1 molecule of oxygen, right? So how would you represent that here in this parentheses right here?
it would be 2/1.
Right, so you're gonna put 2 atoms of oxygen and 1 molecule of O2. That's it. This will cancel out with that. And then we do the calculation, so that's 2 times 6.02 times 10 to the 23 times 2. And according to my calculation, this works out to be equal to 2.41 times 10 to the 24 oxygen atoms. And that's how that is done. All right? Any questions about this one? Any questions? Questions? Okay. Okay, we talked about molar mass already, so I won't go through that. Let's look at the assignment again. And let's see, question number part 2. Okay, so now based on what we have covered, you should be able to do these questions. I'm going to help you out with the first one. So the question said, how many moles are in 25 grams of water? So we start off with 25 grams of water. And the question is, what do we multiply this by? All right. So my question to you is, what goes down here? What goes up here? Well, what would be the denominator down here? And what would be the numerator above? Somebody should be able to tell me what will be here, what will be at the top here, and what will be down here. Come on, folks, it should be able to do this based on what we have just looked at in the PowerPoint.
It would be 1 mole over the atomic mass of water, which is 18 grams.
18.02 grams to be more
Oh,
specific.
02, okay.
Okay, and that's it. So let's see what this gives. 25 divided by 18.02. So according to my calculation, this works out to be equal to 1.4 moles of H2, right? So basically, if you understand how to do that, then you should be able to do the others. So what I want you guys to do right now, just do something here. I want you guys right now to try and do questions 1 through. Okay, I'll say for now 1 through 7. And if you have any questions while you're doing that, please feel free to let me know. All right, so I'm going to give you a couple of minutes to do those problems. So, yeah. Um, all right, so let's see what you have done so far. Let's look at number 2. How many grams are in 4.5 moles of lithium oxide? So how would you do that? Let me break this down a bit. Any ideas?
First found the molar mass.
Mm-hmm. So you found the molar mass of lithium oxide. So that's 2 times, let's see from here. 2 times 6.94. Grams per plus oxygen, which is 16.00 grams per mole. And that gives 29.88 grams per mole. Okay, so what next?
Divided by 12.5.
Okay, so 4.5 moles multiplied by 29.88 over 1 mole, and this is grams, and that's it. This cancels with that. So 29.88 times 4.5. So according to my calculation, this works out to be 6.64. Let me make sure I'm doing the right thing here. 6.94 times 2. Oh, actually, this is not correct. 4.5 times 29.88. That's equal to 130. I don't know where I got that number from. 130 grams, right? That's how that is done. Okay, what about number 3? Anybody try number 3? How would you go about with number 3? Starting off with 23 moles of O2. And the question is asking for how many molecules are there in 23 moles of O2?
Can we go back to question 2 for a minute?
It's there.
So I didn't get 130 grams. I got 134.46.
Yes, so what I did was that I rounded off the answer to 2 sig figs because we have 2 sig figs here.
Okay.
So that's why it's 130.
Okay, thank you.
Okay, so who tried number 3?
Is that 1.38506 times 10 to the 25th?
I'm sorry, repeat that?
Is that 1.38506 times 10 to the 25th power?
You mean that's the answer?
Yes.
Well, I want to find out how you got to that answer. Yes, sir. Oh, all right.
So 23 moles times Avogadro's number.
Okay, so 6.02 times 10 to the 23 molecules of O2, and down here you'd have what?
Oh, 1 mole.
1 mole of O2, exactly. So that will cancel that. So let's see what that gives. 23 times 6.02 times 10 to the 23. And you said 3.82, right?
No,
Oh, wait a minute, hold on, hold on, I did something wrong. 23 times 6.02 times 10 to the 23. Okay, I got 1.38 times 10 to the 25. That's what you got?
yes.
Yes. Molecules of O2, okay. All right, very good. Okay, let's see here, let me scroll down. Okay, I take it I can clear all these drawings here, right? So let me clear this. Let me do that, and let me scroll down. And let's look at number 4. So number 4 is asking how many moles are in 3.4 times 10 to the 23 molecules of H2SO4. So how would you do that? Start off with 3.4 times 10 to the 23 molecules of H2SO4. So what would you multiply this by? What would go up top here? What would go below here? Well, well, what would go up top here as a numerator?
It would be 1 mole.
I'm sorry?
It would be 1 mole.
1 mole of H2SO4, right?
Yep. And it would be Avogadro's number.
Exactly, 6.02 times 10 to the 23 molecules of H2SO4, all right? And let's see what that gives. So that's 3.4, oops, 3.4 times 10 to the 23 divided by 6.02 times 10 to the 23. And according to my calculations, round out to 2 sig figs, the answer is going to be 0.56 moles of H2SO4. All right? And that's how you do that. Okay, what about number 5? They gave you 25 grams of ammonia, and they're asking for the number of molecules. So this looks like a 2-step process, because I would go from grams of ammonia to moles of ammonia. and then from moles of ammonia to molecules of ammonia. Right? So my question is, how would you start this up? How would you go from grams to moles of ammonia? How would you represent that here in this conversion factor? What would go up top and what would go below?
The top would be 1 mole of NH3, and the bottom would be the atomic mass of that
Well, the molar mass to be more.
molar mass.
Yeah, and if I remember correctly, the molar mass of ammonia is about 17.03 grams of ammonia, right? Okay, so you're correct. This will cancel out with that. So we have achieved the first step. The next step is to go from moles of ammonia to molecules of ammonia. So how would you represent that here? Okay, so what goes up, what goes down here? 1 mole of ammonia, and what goes up top? 6.02 times 10 to the 23 ammonia molecules. Okay, and that's the setup. So let's do the calculation. 25 divided by 17.03, and then I multiply by Avogadro's number. And according to my calculation, this works out to be 8.8 times 10 to the 23 molecules. Do this again. 25 divided by 17.03 times 6. Oops. 6.02 times 10 to the 23. Yeah, that's what I got. All right. Okay. I'm going to stop here for today, but I want you guys to keep on working on these questions. Let me see. Hold on. Let me clear this. So I want you to continue. We just did number 5. So make sure you do 6, 7, 8, 9. 10. Let me see here, 11. Okay, so I want you to do up to 11, right? Because for the rest of it, there's some things we have to discuss. I want to make sure that you understand the whole concept of empirical formula before we move on to part 3, all right? So make sure you do all of those questions. And if you have any questions while doing them, please feel free to contact me during my office hours. You can come in person or you can contact me via Skype. All right. Okay. And also, again, just remind you again, make sure you do the test. It's available in the testing center for test number 2. And test number 2 is based on chapters 4, 5, and 6. Right. And if you have any issues during the test, or sometimes, I don't know, sometimes some things happen in the testing center, please feel free to call me and let me know as soon as possible, right? Okay, folks, that's it for today. And for you guys out there in Zoom, I'll be signing off now.
Testing the homework, can I show the work like this?
Oh, yeah, yeah.
Oh,
Yeah, make sure, yeah. In fact, you did a pretty good job of that. Yeah. This should be 0.26. I think this was 0.56.
okay.
Yeah, but yeah, make sure you show the work. Just like that.
I was doing it like that because, oh, right, a 0 before a decimal is not a 6.
Exactly.
I
Yeah,
forgot
exactly.
about that. Yeah,
Any zeros before the first non-zero digit is not significant.
I completely forgot.
Yeah.
So are we
Yeah.
submitting all the way up until chapter 3? I mean, part 3 this Friday?
I'm sorry?
This assignment, is it all the way up to part 3 that we're submitting Friday, or are we submitting the
No,
whole
you're not
thing?
submitting. You're going to keep it because we need to continue working through the other questions next week.
Okay, so we're not submitting anything this week.
No, we're not submitting anything, no.
Okay, thank you.
No problem.